Hello, everyone. This is Pramod Vadrivu. We have our guest speaker here is Mr. Efren Rodriguez. He's a high school science teacher from South Texas ISD, and he actually taught computer science, physics, as well as chemistry. So he's well versed with a lot of science topics, and he's also a Google expert as well. He provides a lot of assistance to a lot of teachers in Texas and around the world. So thanks for joining us. So let's
My
talk
pleasure.
about computational thinking. So like I was explaining you, we are actually talking about computational thinking, and we're also talking about computational thinking in terms of how it can be applied across all curriculums. So so as a science teacher, I'm curious to take your take as well on how we can potentially apply some of these computational thinking elements like abstraction, decomposition, pattern recognition, and learn concepts from science, learn concepts from physics or chemistry, in a better way, right?
Right.
So can we actually use these and learn better concepts in chemistry? So what's your general take on that?
Well, I think especially like you mentioned for chemistry, that's my main subject that I would teach, and I think it really applies to chemistry along with all the other sciences, especially when you're talking about, for example, the atom making compounds and so on. We really can't see those things,
Mhm.
right? So the whole thing is abstract to begin with.
Sure.
But when you start looking at it within the computational thinking part is, okay, well, how could we look at it when we're breaking things down? And again, we can look at problems that we do in physics. We can do problems that we're going to do in chemistry, right? Obviously, in computer science, we always think about, how we're going to break this apart, how are we going to work with it, right? What sequence are we going to go through, right, to get that algorithm that we've got? So let's just start with maybe writing a chemical formula,
Okay.
right? To come up with a chemical equation.
Mhm.
So if they give us some type of word equation that we have to figure out a chemical reaction for, right? We got the reactants, we got the products. How do we get the symbols for those, right? And this is where I would think about first off the abstraction part. Like, well, okay, let's say we're going to make sodium chloride. Well, what do we know about sodium chloride? Well, it's made out of two elements. You've got your sodium and your chlorine. So how are these coming together? So we really have to break this down, right? We want to decompose it, right?
Sure.
Where are these things coming from? So we know, and again, this is all leading up from the beginning of when we start learning chemistry in the classroom. And chemical equations is one of the towards the end that we end up with. So we know, for example, sodium is a metal,
Right.
right? And chlorine is a nonmetal. Well, where are they located on the periodic table, right? So this is where we start getting to pattern recognition.
Right.
Okay, well, we know, okay, sodium is in the first group of elements, right? And our chlorine is in group 7A or 17, depending on how you're looking at your periodic table. Okay, so they're in those individual groups. Well, what do we know about those groups?
Mhm.
So for example, sodium, right? It's in the first group, so we know that normally the metals in that group take on a positive one charge. And chlorine in the non-metal group of the halogens takes on a negative one charge. How did they get those charges? Well, that's where the abstraction comes in, right? Students start recognizing the patterns of positive one, negative one. We're not looking back at, well, how are the electrons set up there, right? What was our Lewis dot structure? What ended up giving us a positive one, negative one, right? So we don't have to, that's where the abstraction, at least I look at it as the abstraction. We don't have to look at all those other things. We've already recognized that based on all those other things, we don't have to go through all those things to remember positive one, negative, right? And then finally, our algorithm for that is we start putting these opposite charges together because again, opposites attract. Now, how many of each do we need, right? Well, we have to end up where we end up canceling the charges. So sodium is a positive one, chlorine is a negative one. So we just need one of each to end up canceling, right? So we end up with what we call a formula unit for our ionic compound. So that's the way I look at how we actually use computational thinking within chemistry. And again, this was just to solve a problem. How do we break it apart? How do we decompose it? And looking at all those things.
Yeah, thanks, Efren. I think that's a very nice way to put computational thinking use in terms of how you would understand a concept, right? So basically, the concept is here understanding how a chemical equation can be put together, or how you can when you take a chemical equation, how you can break it into or decompose into multiple things like metals, non-metals, and try
Right.
to identify a pattern, right? So maybe we can take like multiple equations, similar equations, and see if we can decompose it in a way and recognize the pattern
Right.
between these similar equations. So would you think? I guess we can say we can learn the concept of decomposing this equation better by applying these computational thinking elements like abstraction,
Right.
decomposition, and everything, right?
Right.
So
So like when you do, for example, when you're shooting something, right, for projectile problems in physics, right? Sometimes people just try to put, okay, here's this one equation that solves everything, but why does that work, right? So that's why we can actually decompose it into the different little sections on what is happening to, for example, if it's a cannonball that's being shot out, right? What happens at the topmost part, right? What happens to your y velocity, your x velocity, and so on.
yeah, so yeah, physics also is another one, right? So where you have formulas like this. So the other beautiful thing about abstraction I thought of was so let's say if you take physics 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 observation. So let's take an observation. So can you actually look at the observation? Can you try to find out what all the possible variables, or what is the possible theorem that is going on in your observation, right? So when you are noting down your observation, you can possibly extract or abstract the theory behind your observation,
Right,
and you can write it down into multiple steps, and that would be a good algorithm. So algorithm is
right,
nothing but it's your theory or theorem, and you can apply the theorem possibly to a different observation,
right,
right? So hopefully we can use this same concept in your labs as well. When I say observation, you can actually take some chemistry lab or physics lab, and without knowing the theory, you can at least you can actually observe a certain thing in your lab.
right,
You can perhaps abstract the theory behind what you're observing,
right. And
and
that's one of the
yeah.
things, like, for example, precipitation reactions,
uh,
like you said, right? As you do several different experiments in the lab, right, you'll start noticing certain elements or their ions, right, don't like to dissolve, right? So that's when you would start ending up with a precipitate. And in some cases, you'll always notice certain compounds that contain a certain element, it will dissolve every time. So, like you said, right, you start noticing things from doing the labs themselves.
Yeah, this is fantastic. I mean, there are so many examples that I can find in science alone. There are so
Yeah,
many things actually. So, if the hope is, I mean, when I was a kid, obviously I never thought of any competition thinking, nothing, right? But I'm hoping, my hope is this generation of kids, when they learn about computational thinking aspects of this, when they're learning science as well, then hopefully after they graduate out of high school and all of that, when they actually become like programmers or some sort of professionals, they can actually write better programs. They can actually take us to a whole different world with this knowledge of computational thinking, is what I'm thinking. So
Right.
it is yet to be seen, because 90% of the kids out there, they don't know, and I mean they may be using this implicitly, but they don't know this explicitly, right?
Right.
So my hope is, with the foundation that we are setting to these kids, they can actually use it to write better programs, or to make better automations in future, is
Or
what
just
I'm
to
thinking.
solve problems in general. That's the
Oh, yeah,
thing,
sure. Yeah.
right? So that way that, because one of the main things, like in chemistry and physics, what I would run across is like, I can't solve this. I was like, why not? Why can't I do this whole thing? Well, you're not supposed to do the whole thing at one time, right? You're supposed to break it down, right? And again, before, right, we were talking about computational thinking. It was just like you mentioned, like you do this automatically, but we never talked about it as specific steps that we have, right? It's like, yeah, okay, it's a big problem, but we don't cover the big problem, right? We break it down, we decompose it into the individual parts, right? And then try to start coming up with solutions, right, for those individual parts.
Yeah. So, I mean, we also talked about computational thinking as a problem-solving framework, right? You can use this to solve any problem out there into these elements. Okay, can you use decomposition? Can you recognize the pattern? Finally, can you put in a step-by-step fashion, and can you write an algorithm? So when you follow these, you can solve any problem out there, right? At a very fundamental level. That is true.
Right.
That is true. Yeah. So if they can do all this, they can become better programmers. Who knows? So yeah. So you're right. We need to cover the basics first. Yeah.
Yeah.
Fantastic. Yeah. Yeah, thanks, Efren. I think this is beautiful, actually. I'm so excited on this concept as well, because I was telling these kids that I actually, without knowing a lot of these, I actually working as a computational thinker for 10 years. Extracting the logic into these. I mean, I was actually working for a manufacturing company that designs buildings. So I was actually looking into the core, looking into what they're doing, and I'm trying to extract the logic, and I was trying to put it in the program. So that
Right.
was my job. So that was basically, it's a computational thinker at work. So I was telling these people, there is so much of computational thinking that's going around the world, solving real problems, and they can use these concepts in their own subjects, in their learning. They can
Yeah.
solve any problem that they face. So I'm excited about the opportunity here. So hopefully they appreciate that, and they can learn better.
This is awesome that you're doing this. So that way students would be exposed to the computational thinking and see how it can be applied to what they're working with right now.
Yeah. All right. Thanks, Efren.
Yeah.
Appreciate it. Thanks a lot.
We'll see ya.